So we are going to work on section 8.7, which is logarithmic and exponential equations. And we'll just do one quick application at the end. So when you are solving a logarithmic equation, first thing you're going to do is you are going to isolate the logarithms on one side of the equation. Then you're going to write the log as a single logarithm. That's what we were doing in the last section. Now we're going to apply that skill. Then you're going to rewrite this equation, the single logarithmic equation, in exponential form. So rewrite the equation in exponential form, and then you solve the resulting equation. Last thing you need to do is check all the solutions to verify that they're within the domain. So remember that for a log, the domain has to be positive, greater than 0. Okay, can't be 0, can't be negative. So that means that argument, when you plug your variable in, the value that you got has to give you a positive result. All right, so let's look at how this works. Here's our first example. So we're going to go ahead and bring that log 5 over to the left-hand side. And so that is going to be, that's going to look like log 2 plus x minus log x minus 2 minus log 5 is equal to 0. So now we can put this into a single log. I have two subtraction signs. So when I put this into a log, I'm going to have my argument is going to be look like a fraction. And I'm going to have 2 plus x in the numerator. Then in the denominator, I'm going to have the 5 multiplied by the x minus 2. It doesn't matter the order that you put those, so I'm going to put the 5 first and the x minus 2 right there. All of that is equal to 0. So you have to now put this into exponential form. Recall that when you have a common log, or that means when there's no log, that the base of the log is not specified, then it's implied that it's a 10. So when I put this into exponential form, it's going to be 2 plus x over 5 times x minus 2 equals 10 to the 0. Now that's in exponential form. Well, anything to the 0 is 1. So this 10 to the 0 is just 1. So when you have a fraction, the easiest thing to do is to clear that fraction. So I'm going to multiply both sides of my equation by that denominator. 5 times x minus 2, and then 5 times x minus 2. So the 5 times x minus 2's, they reduce. And so then I'm left with 2 plus x equals 5x minus 10. I can just go ahead and simplify this. I'm going to start by subtracting x from both sides. So then I'm left with 2 is equal to 4x minus 10. Then I'm going to add 10 to both sides. So I get 12 equals 4x. Divide both sides by 4, and I get x is equal to 3. So if I take that 3, and I just want to check this, so I'm going to take the 3 and substitute it in for that first x, and that would give me 2 plus 3, which is 5. That's fine. That's greater than 0. Then I'm going to substitute it in to my next argument, 3 minus 2 is 1. That works. All right, I'm all good. Okay, so this is a good solution. All right, let's go ahead and look at this next one. So for this one, I just have 2 logs on the left. So I'm going to bring those together and put them into a single logarithm. So that's going to be log base 2, then 3x minus 2 over x minus 5 is equal to 4. My next step is to put this in exponential form. So that is, I'm going to bring this 2 over, so it's going to be the base of that 4. So it's going to be 2 to the 4th is equal to 3x minus 2 over x minus 5. Well, 2 to the 4th is 16. So I'm just going to change that to 16. Now I'm going to multiply both sides by that denominator, x minus 5, and then x minus 5. So on the right, those x minus 5s reduce. On the left, the 16 is going to get distributed. So we have 16x minus 80 is equal to 3x minus 2. So I'm going to go ahead here and I've got, I'm going to subtract 3x from both sides. And so I end up with 13x minus 80 is equal to a negative 2. I'm going to add 80 to both sides. And so then I end up with 13x is equal to 78. Divide both sides by 13, x is equal to 6. So when I check this, I'm just going to go back to my original problem, put a 6 in for both of those arguments. And so for the first one, I get 18 minus 2, which is 16. That's fine. For the next one, I get 6 minus 5, which is 1. That's fine too. So this checks out, and that's a good solution. All right, let's do one with a natural log. Remember, a natural log is a log. And so everything that I do is going to be exactly the same process. The first thing I want to do is put this into a single logarithm. So this one is a little different because I don't have any subtraction signs. So this one, I'm just going to take and multiply my 2 arguments. So it's going to be natural log of 2 times x minus 1 is equal to 0. So remember that the natural log is log base e. So when I put this into exponential form, well, here, let me, just because I know some people are visual and need to see that. So I could substitute log base e for natural log. Okay, if that's helpful to you, then do it. Okay, but now when I put this in exponential form, it's going to be e to the 0 is equal to 2 times x minus 1. Well, anything to the 0 is 1. So e to the 0 is no different. That's equal to 1. I'm going to distribute on the right that 2. So that'll be 2x minus 2. Then I'm going to add 2 to both sides. So I get 3 equals 2x. Divide both sides by 2. And 3/2 is equal to x. 3/2 is the same as 1.5. So when I go back to check this, okay, I'm going to take 1.5 minus 1 still leaves me with a half, and that is greater than 0. So this is a good answer. And I would keep my answer as the fraction. All right. Let's solve this next one. It's a natural log, but it also has that square root, which makes it a little different than any of them that we've done so far, but not impossible. All right. So let's go ahead and do this one. So this is going to be, well, first thing I'm going to do is take and convert that square root to fractional exponent. So that'll be the natural log x plus 6 raised to the 1/2 is equal to 9. Now I'm going to take this 1/2 and pull it out front. So I've got 1/2 natural log x plus 6 equals 9. Well, I need to have that natural log isolated. So the way I do that is I am going to multiply both sides of my equation by 2. And that is going to reduce that 1/2 in front of that natural log. And then on the right, I've got an 18. So my next step is to put this in exponential form. So the natural log is a log base e. So this is going to be x plus 6 is equal to e to the 18th. Subtract 6 from both sides. X is equal to e to the 18th minus 6. If I want to check that, I'm just going to go ahead and I'm going to take the square root of x plus 6, and I'm going to substitute in for that x this e to the 18th minus 6. So that's going to be the square root of e to the 18 minus 6, and then I've got this plus 6. Well, minus 6 plus 6 is 0, so I end up with the square root of e to the 18th. I don't even have to do that calculation. I could put it in my calculator, but I know that e is going to be 2.718 raised to the 18th. That's going to give me a positive number. So that's all I care about, is that my argument of my log is positive. I don't need to know the exact number when I'm checking it. I just need to know that it's positive, that it is. So it checks. All right, let's move on. So I'm going to show you a shortcut that works for a certain type of logarithmic equation. And this is going to be when we're able to use an idea of equivalency. So equivalency is going to happen when you have logs on both sides of the equation. So for example, if I've got log base b of x equal to log base b of y, okay? So I note that my bases are the same. And so this implies that my arguments would have to be the same, because that's the concept behind an equal sign, that both sides of that equal sign are equivalent. So that implies that x has to equal y. Well, here's how we can apply that to a logarithmic equation, but we can only apply it when we have logs on both sides of our equation. Okay, so for this first example here, problem number 4, let's go ahead and on the left, I am going to put those two logs into one single log. So that's going to be log of 5 plus x over x minus 5 is equal to log 3. So I have exactly the same common log on both sides of my equation. They have the same base 10. So my arguments can be set equal to each other. So I can take 5 plus x over x minus 5 equal to 3. And now I just solved that. So I'm going to multiply both sides of my equation by that denominator, x minus 5. So then on the left, my x minus 5's reduce. So then I'm left with 5 plus x equals, I'm going to distribute that 3x minus 15. Well, this is a simple problem for us to solve. I'm going to first start by subtracting x, and so that's going to give me 5 equal to 2x minus 15. Now I'm going to add 15, and so that is going to give me 20 is equal to 2x. Divide by 2, x is equal to 10. If I substitute a 10 into my original arguments, okay, put a 10, I just need to be concerned that those arguments are going to be positive, and they are, both of them are. So this is a good solution. All right, let's look at the next one. We have natural logs. Natural logs work too. They're still logs. So let's go ahead and we're going to put these into, on the right, into a single logarithm. So on the left, we've got natural log of 3x equals natural log of 4 times x minus 3. Okay, so that means that my arguments can be set equal to each other. So 3x equals 4x minus 12. I like to keep my x's positive, so I'm going to subtract 3x. That gives me 0 equals x minus 12. Then I'm going to add 12. So I have 12 is equal to x. If I go ahead and substitute that into my argument, I get 12 minus 3, which is 9. No problem. This checks out. All right, last one in terms of this equivalency. Well, not quite the last one. Last one on here, and then I'm going to give you an extra one. All right, so I'm going to go ahead, set these equal to each other because I have the same base with these logs. So 6x plus 2 equals 6x plus 7. If I subtract 6x from both sides, I get 2 equals 7. Well, that's not true. That's false. So when you get a false statement, then that means there's no solution. Let me give you another one to try. It's kind of interesting. All right, how about if we have, we're going to try this. So we'll call this one 6.5, okay? I'm going to write this one in gray. So it's another example, and it's log base 3 of x minus 8 equals 2 minus log base 3x. Okay. So for this one, it might seem like we should be able to have equivalency because I have a log on both sides, but I can't. I can't have equivalency because of this 2. In order to use equivalency, I can only have log. Okay? So I'm going to have to use the other method, which is to bring all of my logs to one side. All right. So I'm going to start by adding log base 3 of x to both sides. So that'll give me log base 3 x minus 8 plus log base 3 x is equal to 2. Now I'm going to bring on the left those logs into a single logarithm. So that'd be log base 3 of x minus 8 times x is equal to 2. I'm going to take and put this in exponential form. So this is going to be x minus 8 times x is equal to 3 raised to the second power. The base of the log becomes the base of my exponent. All right, well, 3 raised to the second power is just 9. I'm going to go ahead and distribute this x. So I get x squared minus 8x equals 9. So I'm going to, I see right away that I have a quadratic, okay? And so I'm thinking, maybe the best way to handle this is to bring all of my terms on one side and set it equal to 0. So that's going to be x squared minus 8x minus 9 is equal to 0. So now I can factor this. This is an easy one to factor. -9, +1. So that's going to be x minus 9, x plus 1 is equal to 0. Use the zero product rule. Set each of those factors equal to 0. X minus 9 equals 0. X plus 1 equals 0. So x equals 9. X equals -1. Now I want to go back and check each of those solutions. If I put a 9 into that first argument, I get 9 minus 8. That works. That gives me a 1. If I put a 9 right there into that x, that works. All right, now let's test -1 as a potential solution. If I put a -1 in for x, I get a -9 for my argument. I don't have to go any further. If that solution does not work for even one of the arguments, then it doesn't work for the entire equation. So this x equals -1 is not part of our solution. We call it extraneous. All right, so our only solution is x equals 9. That happens sometimes. That's why I wanted to do that one so you could see it. All right, let's continue on. But now what we're going to do is we're going to solve exponential equations. So just like we ended with talking about equivalency for logarithmic equations, we're going to look at the equivalency for exponential equations. Okay, so what this says, and we've actually used this, we just didn't say it was a definition. Okay, so when your bases are the same, then that implies in an equation that your exponents have to be the same. They might not look the same at first, okay? 3 times 2 might be on one side and 6 might be on the other, but that's equivalent. All right, so we can use this to solve equations. Let's take this first example here. So we have got 3 raised to the x plus 8 equals 27. What I want to do is I want to convert 27 to an exponent that has a base of 3. Well, that would be 3 cubed. So now I have 3 raised to the x plus 8 is equal to 3 raised to the third. I can set these exponents equal to each other. X plus 8 is equal to 3. Subtract 8 from both sides, and I get x equals -5. I don't have to check anything. All numbers in my domain are going to work. Okay, so x equals -5 is perfectly fine solution. Let's look at number 8. So with number 8, this one's kind of fun. All right, I see here a base of 2. I would really like a base of 2 with the 1/8. So how do I get that? Well, I know that I can take that 8 and 2 cubed is equal to 8. So I can change that to 1 over 2 cubed raised to the x is equal to 2 to the x minus 4. I'm getting close. If I can take that now 2 to the third that's in the denominator, and I'm going to put it in the numerator. And when I do that, the exponent is going to go from a positive 3 to a negative 3. So that's 2 to the negative 3 raised to the x is equal to 2 to the x minus 4. Okay. Well, I know from my properties of integer exponents that when I have a power and an exponent, I just multiply them. So that means, since I have my bases that are the same, that I have a negative 3x equal to x minus 4. So I'm just going to start by subtracting x from both sides. And so that gives me a negative 4x equals a negative 4. Divide both sides by negative 4. X is equal to 1. There we go. All right, I want to do one more in here. It's another little bonus problem, okay? So extra problem, extra example, right here in the middle. And that's going to be 2 to the x times x plus 3, that's my exponent, equals 1/4, okay? Well, I'm going to first take that 1/4. So I've got 2 to the x times x plus 3 equals, I know that 4 is the same as 2 squared. And so if I bring that to the numerator, it's going to be 2 to the negative 2. So now I have my common base of 2, so I can set my exponents equal to each other. X times x plus 3 equals negative 2. I'm going to go ahead, distribute that x on the left, x squared plus 3x. Now at the same time, I'm going to add 2. So I've got my whole quadratic equation equal to 0. Now I just factor x plus 2, x plus 1 equals 0. When I set both of those factors equal to 0, I get x is equal to negative 2 and negative 1. I don't have to worry about checking them. All real numbers are part of the domain for our exponential functions. All right. Well, what happens when we can't convert our numbers and create this equivalency situation? What do we do then? Well, what you do is you would isolate one of the exponential expressions in the equation. So you get one of the exponents on one side. Then you're going to take a logarithm on both sides of the equation. And then you're going to use the power property to write the exponents as factors. And then you solve the resulting equation. Wow, seems like a lot. Okay, here we go. So I'm going to, on the right, do this example, but instead of using a natural log, I'm just going to use the common log. All right? And I'm going to show you that it doesn't matter whether you use natural log or common log, you get the same answer. So I'm going to write log. First step is to take a log of both sides. So log 2x plus 8, okay, equals log 3. So now what I'm going to do is I am going to go ahead and use the power rule to bring that x plus 8 out in front. So it's going to be x plus 8. I put parentheses around it because it's that entire exponent, that entire expression that is acting as the exponent. So x plus 8 times log 2 equals log 3. Okay, I'm going to go ahead and I'm going to divide both sides by log 2. Okay, log 2, like that. So I'm left with x plus 8 equals this log 3 over log 2. I want x to be all by itself, so I get x is equal to that log 3 over log 2 minus 8. And that's my answer. That's actually exactly what they got. And you might be, wait. But they got natural log over natural log. Remember, it doesn't matter. That's a ratio. We saw it with change of base. As long as it's a log over a log and the logs have the same base, you're going to get the same answer. So log 3 over log 2 is going to give you exactly the same thing as natural log 3 over natural log 2. Pretty cool. All right. Now, what I tend to do is when I have irrational number e, okay, then I tend to take the natural log of both sides. So I'm going to rewrite this as natural log e to the 2x equals natural log of 7. And now I'm going to use the power rule, bring that 2x out front. So that's going to be 2x natural log e equals natural log 7. Well, natural log e is 1. Why is that? Because that's the same as as log base e of e. And when when the base of your log matches your argument, that is equal to 1. So this becomes 2x is equal to natural log 7. I want x all by itself, so I'm going to divide both sides by 2. X is equal to natural log 7 over 2. It's not asking me to round anything. So that means it wants this as an exact answer. So that's my exact form. If it was asking me to round to the nearest tenth, like it's asking in this next problem, then that means I need to find the decimal. All right, so let's solve this equation. So because this one has, it has numbers in exponential form, but no natural logs, or no e's, I'm going to take the log of both sides. So I'm going to take the log of 9 to the x equals log of 14. I'm going to take this x, put it out front. So x log 9 equals log 14. Divide both sides by log 9. So x is equal to log 14 over log 9. And that is approximately, let me look at my notes. When I round, you get approximately 1.2. Okay. Let's look at one more here. Okay. This is a fun one. Number 11. So for this one, I'm going to take the log of both sides. So log of 4 to the x equals log 5 to the x minus 5. Now I'm going to apply the power rule to both of those, both sides. So it'll be x log 4 equals x minus 5 log 5. I'm going to go ahead on the right and distribute. Wow, this is going to feel weird. So this is how I'm going to distribute. I'm going to take that log 5, multiply it times x. Take the log 5, multiply it times 5. And so that's going to give me x log 5 minus 5 log 5. Gosh, this seems like a mess. But here's how I want you to look at it. I want you to look for the unknowns. Look for the variables. Look for the x. And so I see I have an x here on the left, and I have an x on the right. What your goal is to get the x's on the same side. So I am going to subtract x log 5. So I got x log 4 minus x log 5 equals negative 5 log 5. So now I have an x as my coefficient for both of those logs. Well, I can take a greatest common factor out. My greatest common factor is x from both of those terms. So I take out an x, and then I'm left with log 4 minus log 5 equals negative 5 log 5. So now I'm going to divide by that expression that's in parentheses, and then I'm going to have x all by itself. I'm going to have x equal to negative 5 log 5 over that quantity log 4 minus log 5. Woof. That one is super cool. Okay? That is your answer. That's your exact answer. It's solved. All right. Let's do this one little story problem here. Okay? So we're looking at the decay of 437 milligrams of an isotope. And our formula that they give us for calculating that decay is right there, where T is time in years. We want to find the amount of this isotope left after 89 years. This is actually very straightforward. All we're going to do is we are going to substitute 89 in for T. So we're looking for the amount left after 89 years. So I take 437 e to the negative 0.014 times 89. Okay? So that is going to give us when I put it into my calculator, it's going to give me 125.70 milligrams. All right. So it's really just a plug and chug for that last one. All right. You have what you need to be successful on this last homework assignment. So just get after it. You're almost done.